Greetings to everyone. In this video, we are going to learn the number system, that is the first chapter of class 9 mathematics. And in this chapter, we are going to learn about the basic of mathematics, that are numbers. Until now, we have come across different kinds of numbers. So in this chapter, we are going to classify these numbers and learn few more about these numbers. And before going into the detail, let me tell the objectives of these chapters. And I've divided this chapter into 4 parts. In the first part, we are going to learn about the classification of numbers, under which we are going to recall the rational numbers that we have learned in class 8. And then we are going to introduce the irrational numbers. And then we are going to learn the how to plot or how to represent these numbers on the number line. In the second part, we are going to discuss the decimal expansion of a real number and type of decimal expansion of a real number, and we are going to learn the successive magnification method to show decimal numbers on the number line. In third part, we are going to learn how to express decimal number in rational form. And fourth one is about the rationalization. It's a whole new thing to the class 9 students. So we are going to discuss this in detail. Now the first one is the classification of a number. Now from the kindergarten, we start counting things, starting from 1 and then move on to 2, 3, 4 and so on. And these numbers are called natural numbers, and it is denoted by capital letter N. And natural numbers are also called as counting numbers, since we normally count any objects or any cash in the starting from 1 and then moving on to 2, 3, 4 and so on. So these numbers are called natural numbers. And the next set of numbers are called whole numbers. And whole numbers you normally denoted by the capital letter W. And this whole number, it includes all the natural numbers and it has 0. So the whole number is a larger group of the natural numbers. We can say that, isn't it? Because whole number includes all the natural numbers, whereas the natural number does not include all the whole numbers. That is 0. 0 is not included in the natural number, but 0 is a whole number. Now the next set of numbers are called integers. And integers are denoted by capital letter Z. And integers include all the whole numbers, and it also includes the negative of our natural numbers, such as -3, -2, -1, so on. We can write towards the left to the infinite. So we can say that the largest whole integer is -1 and the smallest integer is -infinity. We cannot define exact number because it keeps on decreasing. And the next set of numbers. Now till here you will see that the integer, it does not include all the decimals and the fraction of our numbers. For example, we have 0.234, 0.1, 19 by 17, 2.333 ... and these dot represent that the decimal number 3 keeps on repeating. It will not stop, or here the remainder does not become 0. So these numbers are not included in integers. Therefore, we need a new group of numbers that we call as rational numbers. And rational numbers are denoted by capital letter Q. Or you can define rational number. We have defined the rational number in class 8. That is a number which can be expressed in the form P by Q, where P and Q are integers and Q not equal to 0. Here, in case of 1 by 2, P is 1 and Q is 2. And 2 is not equal to 0. Therefore, 1 by 2 is a rational. 3 by 2 is a rational. Similarly, 0.234 is a decimal number and it can be expressed as a rational, that is 234 by 1000. Therefore, decimal can be expressed in the rational numbers. So these numbers are called rational numbers. But important point to keep in mind is, now you'll see that in 0.234, the decimal place of the number terminates after 3 place of decimal, and in case of 0.1, you'll see that decimal place stops or terminates after 1 place of decimals. But in case of 2.3333 so on, here the decimal place is not terminating, but it is repeating, because same number is being repeated over here. And these numbers can be expressed in the form P by Q. Therefore, they are called rational numbers. Now, there are some numbers which cannot be expressed in the form P by Q. For example, root 2, root 3, root 5 and pi. Now, these numbers cannot be expressed in the form P by Q. And these numbers are called irrational number, which is opposite of the rational numbers. And so we need a new group of numbers, a larger group of numbers, and this group is called real numbers. And real numbers are denoted by capital letter R. So we can define real number as a collection of rational number, and irrational numbers are called real numbers. So we can say that all the natural numbers are whole, all the natural numbers are integer, all the natural numbers are rational numbers, and all the natural numbers are real numbers. But all the real numbers need not be rational, all the real numbers need not be integer, and all the real number need not be whole number, and all the real number need not be a natural numbers. Therefore, reverse process is not true in this case. Now, to have a better understanding, let's take an example. For example, this man. Now, he lives in Lhasa. So, we can say that this person lives in Tibet, because Lhasa is in Tibet, since Lhasa is the capital city of Tibet. And again, we can say that this person lives in Asia, because Tibet is in Asia. And further, we can say that this person lives on the earth, because Asia is on the earth. Now we'll see the reverse process. For example, there are two sisters. Now these two sisters, we can say that they live on earth. But it is not necessary that they live on Asia, because they might be on the North America, South America, Australia, Antarctica or Europe. So any continent we can take. They might be on any of these continents. And these two sisters, they need not be in Tibet also, because they can be in India, they can be in California, etc. So the reverse process is again not true over here. Similarly, while discussing about the number system, we are talking about the numbers. For example, a number x is a natural number. Now this number x is a natural number. So we can say that this x is also a whole number, because whole number is a collection of natural number and 0. Again, we can say that this x is a integer, because integer is a collection of whole number and negative natural numbers. Again, we can say that x is a rational number, because rational numbers are the collection of integers and the number in the form p by q. Again, we can say that x is also a real number, because all the rational numbers are real number. But the reverse process is not true. Let's take an example. For example, this number x is a rational number. It is given that the given number x is a rational number. But this rational number is not necessary to be integer. It is not necessary to be whole number, and it is not necessary that the given number x is a natural number. So the reverse process is not true. For example, if x is equal to 0.5, then it is not integer, and 0.5 is not a whole number. 0.5 is not natural number. Since we have said it is not necessary, but sometimes it can be an integer, it can be a whole, or it can be a natural number. For example, let's take number 1. 1 is a rational number because it can be expressed in the form p by q, that is 1 by 1, which is equal to 1. So 1 is an integer, 1 is a whole number, and 1 is a natural number. Therefore, it is very important that the given number x is not necessary to be integer, to be whole, or to be natural. But it can be integer, it can be whole number, or it can be natural number. By looking at the value of x, you can say that. I hope you have understand clear till here, and in the next slide we'll take some examples. In the first column we have some numbers: 500, minus 2, 0.15, 0, root 3, 3 by 7, and minus 1.5. In the second column we'll see, or we'll check whether the given number is a natural or not. In the third, we will see whether these numbers are whole number or not. In the fourth, we see whether these numbers are integer or not. And in the fifth column, we'll see whether these numbers are rational or not. And in the last column, we'll see whether these are real number or not. Now, we know that all the natural numbers are whole number. All the natural numbers are integer. All the natural numbers are rational. All the natural numbers are real number. But all the real number need not be a rational, all the real number need not be an integer, all the real number need not be a whole number, and all the real number need not be a natural number. Similarly, you can apply that to the integers also. All the integers are rational, all the integers are real, but all the integers need not be a whole number, and all the integers need not be a natural numbers. For example, the first one is the 500. 500 is a natural number. So, if the given number is a natural number, then it is a whole number, it is an integer, it is a rational number, it is a real number. And the next example is minus 2. Minus 2 or the negative 2 is not a natural number, it is not a whole number. Since whole number includes natural and 0. Since it is not a natural and minus 2 is not a 0, therefore it is not a whole number. And it is a integer because minus 2 is the negative of a natural number. That is, 2 is a natural number and we have negative sign over here. So minus 2 is a negative of a natural number. In the definition of integer, we have said that integers are the collection of whole numbers and negative natural number. So here we have a negative natural number, therefore it is an integer. So if the given number is an integer, then it is also a rational number and it is also a real number. Now next one is 0.15. 0.15 is not a natural number, it's not a whole number, it's not a integer, because natural numbers are the collection of numbers such as 1, 2, 3, 4 and so on. It does not include the decimal numbers, and also in the whole number it does not include the decimal numbers, and also in the integers it does not include decimal numbers or the number in the fraction form. Therefore, it is a rational numbers because 0.15 can be expressed as 15 by 100. Therefore, it is a rational number. And if the given number is a rational number, then it is also a real number. Now, the fourth example is 0. Now, 0 is not a natural number because natural number includes numbers such as 1, 2, 3, 4 and so on. It does not include 0. But 0 is a whole number. When we define whole number, we have mentioned that whole numbers are the collection of natural number and 0. Therefore, 0 is a whole number. And every whole number is a integer, every whole number is a rational, and every whole number is a real. And next one is square root of 3. Now, in natural number, we don't have a square root of a number. or square root of 3 is equal to 1.73. So it keeps on going and it will not terminate. So square root of 3 is not a natural number. Square root of 3 is not a whole number. Square root of 3 is not an integer, and square root of 3 is not a rational number, because root 3 cannot be expressed in the form p by q. Therefore, now root of 3 is a real number, or we can say it is a irrational number, and irrational numbers are included in the group real number. Similarly, you check for the 3 by 7 and 1 minus 1.5. So here we'll define the rational number, or recall the rational number that we have learned in class 8. Rational numbers are denoted by a capital letter Q, and we can define it as a number which can be expressed in the form p by q, where p and q are integers and q not equal to 0. Now this is very important point over here. P and q are, it should be an integer and q should not be equal to 0, because for example any number divided by 0 is not defined. Therefore we cannot find 1 divided by 0 or 2 divided by 0, etc. Therefore q should not be equal to 0. Let's take few examples of a rational number. For example 2. Now this 2 can be expressed as 2 by 1. And 2 by 1 means 2 divided by 1. So we'll get 1 2s are 2, is subtracted, and then you'll get 0. Therefore 2 is a rational number because it can be expressed in the form p by q. Here p is equal to 2 and q is equal to 1, and 2 and 1 both are integers, and q1 is not equal to 0. Therefore 2 is a rational number. Let's take a second example, that is 0.5. Now this is a decimal number, and 0.5 can be expressed as 5 by 10, because when you move the point towards the right, then you add 1 0 at the denominator. So 5 by 10. Now 5 and 10 has a common factor, that is 5. So we'll divide both numerator and denominator by 5. 5 1 is 5. 5 2s are 10. Therefore 1 by 2. That means 0.5 can be expressed as 1 by 2, where 1 and 2 are integers and 2 is not equal to 0. Therefore it is a rational. Now till here we are done with the rational numbers, and we have already defined rational numbers also. Now there are some numbers which cannot be expressed in the form p by q, where p and q are integers and q not equal to 0. For example, we have a square root of 2 which is equal to 1.41423562, and it keeps on going and will not terminate. Therefore such numbers are called irrational numbers. And square root of 2 cannot express in the form p by q. So now we have two separate group of numbers, that are rational number and irrational number. Rational number includes all the integers, it includes all the whole number, it includes all the natural numbers. But here on the other hand, we have a totally different set of numbers called irrational numbers. Now those numbers which cannot be expressed in the form p by q. So when we combine these two numbers together, we get a new set of, or a group of number called real numbers. So we can define real number as a collection of all rational number and irrational number are called real numbers. We can take few examples: 1, 1.5, 1 by 2, 10 by 3, 22 by 7, 7, root 2, root 3 and pi. Now in this, still you can add few more examples if you want to. Now in these examples, 1 is a rational, 1.5 is a rational, 1 by 2 is a rational, 10 by 3 is a rational, 22 by 7 is a rational, and root 2, root 3 and pi are irrational numbers. So Rational numbers and irrational number together form a real numbers. Now things to be keep in mind is square root of any number which is not a perfect square are called irrational number. For example, 4 is a perfect square number and square root of 4 is 2. Therefore, square root of 4 is not a irrational number. It is a rational number. So things you should keep in mind that square root of any number which is not a perfect square is a irrational number. Now in the next part we'll discuss about how to show the real numbers on the number line. And real numbers are broadly classified as rational numbers and irrational numbers. So first we'll discuss the rational number on the number line. And we have learnt about how to represent rational number on a number line and how to find a rational number between two given rational number in class 8. So to recall, I'll do one example here. The question says represent 4 by 5 on a number line. Now 4 by 5 on a number line. So first we'll draw a number line, and on the number line each point represent a certain number. So to show 4 by 5 on a number line, we have drawn a number line and will mark few points, and these points are equally spaced. That means square between first and the second, and the space between the second and the third are equal. It should be equally spaced. So we'll label them as 0, 1 and 2. And here the 4 by 5. You'll see that the numerator 4 is less than denominator 5. Since denominator is greater than the numerator, so this number lies between 0 and 1. Now how to represent it over here between these two, 0 and 1? First thing is you'll check for the denominator. Here denominator is 5. So we'll divide this line into 5 equal parts. 1, 2, 3, 4 and 5. We have divided this line segment into 5 equal parts. So 0 means 0 divided by 5 is 0. So the first number is 1 by 5, 2 by 5, 3 by 5, 4 by 5, and the 5 by 5 is equal to 1. And this is our required number on the number line. Similarly, you can take a break for 10 minutes and try to represent the following numbers on the number line. A 3 by 7, B 8 by 3, C minus 5 by 3, D 8 by 6, E 0.25 on the number line. So in the next part, we are going to discuss about the irrational number on the number line. Now this method is also called the spiral method to show irrational number on the number line. Here I'll show irrational number root 2 and root 3 on the number line. Now how to do is, first we'll draw a number line. On this number line, with the help of a compass, take a radius, any radius suitable to your page, and mark few points so that the distance between each points are equal. You don't have to use the scale or the centimeter scale to measure. It will be difficult. And we'll name these points. The first point is 0. Since these two numbers are positive, so it lies at the right hand side of the 0. We have 0, 1, 2, 3 and 4. Now to draw a root 2 or to represent root 2, what we do is from 1 draw a line perpendicular to it. So we'll draw a line perpendicular to the given line at 1, and we have learned how to construct a perpendicular at a point in the lower classes. So we'll join these 2 points, 1 and this point. Okay. Now to make root 2, what we do is measure the length of 0 and 1. 0 and 1. 1 unit we take and mark 1 unit on the perpendicular line that we have drawn. Here it goes. And join the 1 unit intersection point from the perpendicular to the 0. And we'll name this point as A and this as B, and 0 let it be O. And we'll extend this line so that we can continue drawing root 3 and so on. Okay, now 0 or OA is equal to 1 unit and AB is also 1 unit. Therefore, OB is square root of 2, and we'll prove that in the later part. So we'll measure OB, that is root 2, and mark this point on the number line. We'll draw an arc passing through the number line. Okay. Now this is our square root of 2. We'll write square root of 2 over here. Done. We are now done with the representing square root of 2 on the number line. Now to represent root 3, what we do is from point B, we'll draw a line perpendicular to OB. Draw a semicircle and then bisect this semicircle. And join the point B to the intersection point here. Let's join this. And again, you'll take a measure of 1 unit on the compass. And from B, take a measure of 1 unit on the perpendicular that we have drawn. And join these 2 points, and we'll name this point as C, and join C to O. Now OB is root 2 and BC is 1 unit, so OC will be our square root of 3. Okay. Now the next one is square root of 4, and we know that square root of 4 is not an irrational number, it is a rational number. Therefore it should pass, square root of 4 means 2, it should pass through 2. So we'll check whether our construction is correct or not. Now we'll do the same thing from point C, draw a perpendicular to OC. And join point C to the intersection point here, the point C to this point. Okay, join this. And again take a measure of 1 unit on a compass, or a radius of 1 unit on a compass, that is between 0 and 1, and to take a measure of 1 unit on that perpendicular line, and we'll name this point as D, and you join O and D. This is therefore CD is 1 unit. CD is 1 unit. Therefore OD is square root of 4. So square root of 4, it should, now this length should pass through 2 on the number line, isn't it? So we'll see whether it's passing through 2 or not. Measure this OD with the help of compass and draw an arc. Now here you see that it passes through 2. Therefore our construction is correct. Now here we'll prove how this OB is square root of 2 and OC is square root of 3. Let's prove it over here. To prove so, we are going to use the Pythagorean theorem. To use the Pythagorean theorem, we need to have a right triangle. So here angle OAB is 90 degrees, similarly OBC is 90 degrees and OCD is also 90 degrees. So each triangle is a right triangle. So in the first case, we'll take in right triangle OAB, that is the shaded portion, OAB, right angle at A. So Pythagoras theorem states that hypotenuse square is equal to perpendicular square plus base square. So opposite to the angle measuring 90 degree, that is OB square is equal to OA square base square plus AB square. OB square equal to OA is 1 unit and AB is also 1 unit square. 1 square is 1 plus 1 square is 1. Therefore OB square equal to 1 plus 1 is 2. So we'll take square root on both sides. Therefore OB is equal to square root of 2. Hence proved. Again we'll try to prove the square root of 3. To prove square root of 3, to prove that OC is the square root of 3, we'll take right triangle OBC. In right triangle OBC, right angle at B. So by using the Pythagoras theorem, hypotenuse is OC. OC square is equal to OB square plus BC square. Therefore, we'll write OC square equal to OB is square root of 2. We have already found it over here. Square plus BC is 1 unit because we have taken 1 unit measure. And square and root get cancelled. Plus 1 square. And you'll get 2 plus 1. Here we have OC square. So OC equal to 3 square will get 3. So to remove the square, we take square root on both sides. And the square and root get cancelled. So we'll get OC equal to root 3. Similarly, you can construct root 5, root 6 and it keeps on going like this. So it's called spiral method. Now till now we have covered the first part of the chapter, that is about the classifications of numbers and how to represent the real numbers on the number line. And here are some questions related to what we have learned so far. And I would request all the students to do it by themselves. Now next part of the chapter is about the decimal expansion of our real numbers. And in this part we are going to learn how to express the given numbers in the decimal form. And also we are going to discuss the types of decimal expansion of our real numbers. And then we are going to learn the successive magnification method to show decimal numbers on the number line. So let's move on to the first part, that is, first topic, that is the decimal expansion of our real numbers. Now we have already learned that real numbers are classified as rational numbers, or irrational numbers. So first we'll take few examples over here and see whether these are rational or irrational. Now in the first example A, we have taken 7 by 2 is equal to 3.5, and 7 is a integer, 2 is a integer, so 7 by 2 is a rational. Again 3 by 4 is also a rational, and 1 by 3 is also a rational, and 20 by 3 is also a rational, and all the rational numbers are real numbers. Now let's see how we get this 3.5. Here we'll do the normal division method, and 7 is the numerator, so it is a dividend, and denominator 2 is called divisor. So when you divide 7 by 2, you'll get 2 3s are 6, subtract 8, you'll get 1. So you mark a point here and then add 1 0, and then 2 5s are 10, and here you see that the remainder becomes 0. So 7 by 2 can be expressed as 3.5, or 3.5 is the decimal expansion of 7 by 2. Similarly, in the case of 3 by 4, we can perform the division method, that is 3 divided by 4. Please keep in mind that numerator is always a dividend and denominator is always a divisor, not vice versa. So when you divide it, 4 0 is 0. So when you subtract 8, you'll get remainder 3, and then you put a point here and then add 1 0 here, and 4 7s are 28. So then again you subtract 8 and then you'll get remainder 2. Again it's not 0 since we have already added point here. So you add 1 0 here, it becomes 20. So 4 5s are 20 and you'll get the remainder 0. Therefore 3 by 4 can be expressed as 0.75, or you can say that 0.75 is the decimal expansion of 3 by 4. Now in the next example C, that is 1 by 3 is equal to 0.333. Let's check this. Okay, here again 1 numerator divided by denominator, that is 3. So when you divide it, 3 0 is 0, and subtract it, you'll get 1, and then you put a point here and add 1 0 over here, it becomes 10. So 3 3s are 9, and then you'll get 1. Again you'll get remainder 1 over here. Since we have already added point here, so you can add 0 here, and 3 3s are 9. Again you'll get remainder 1. Since point is already added, so we'll add 1 0. Again 3 3s are 9, and you'll get remainder 1. So if you keep on doing this, it will not stop, or you can say that remainder will never become 0 over here. But the thing is, here after the decimal point, the number is repeating. Here you see that 0.333. Again, if you add 0 here, we'll write 3 here. So 3 is repeating over here, and you can write it as 0.333, and or you can write it as 0.3 bar. We'll discuss that in the next part. Again, similarly, in the example D, you'll find 20 by 3. 20 by 3, when you express it in the decimal form, you will get 6.666666, and it will not terminate. So the first two cases, the decimal expansions are terminating, because you see that at the end the remainders become 0. Therefore, these decimal expansions are called terminating decimal expansion. And in the next two examples, that is C and D, in both the cases you will see that the decimal points are not terminating. At the same time, it is repeating. So such kind of decimal expansions are called non-terminating and recurring decimal expansion, or you can say repeating decimal expansion. So every rational number will have either terminating decimal expansion or non-terminating and recurring decimal expansion. Now, how to find the decimal expansion of an irrational number? So in class 8 we have learned about how to find the square root of 2 or square root of any number by long division method. So same here, again we'll use the long division method to find the square root of a number. Let's take example square root of 2. Now square root of 2 means 2 raised to the power 1 by 2. Root means power of 1 by 2. If it is a cube root, then the power is 1 by 3. Now how to find this? We'll show a long division method over here. Now we'll write 2 first and then make a box like this. And after the decimal point, we can add as many zeros as you like. So we'll add 2, 3, 4, 5, 6, 7, 8 zeros. That means we can find the decimal up to 4 places of decimal. If you want to find 5th place of decimal, you have to add 2 more zeros. And now the important thing over here is numbers after the decimal points are grouped from left to right, or they are made in a group of pair from left to right. So we'll make a group like this. And now here you have to find a number which when multiplied with itself, it should give either 2 or less than 2, not more than 2. So we'll see that 1 is 1 and 2 2s are 4. So 4 is more than 2. Therefore we'll take 1. 1, 1. So 1 into 1 is 1. So you subtract it, you'll get remainder 1. Move the point upward over here, and then we have already made the group, so we'll take 2 zeros down. Now the next step is, here what you have to do is you have to add 1 over here. Here we have 1, therefore we add 1 here. So when you add 1 and 1, you'll get 2. Next step is, now you have to find a suitable number over here in the unit place, so that when you multiply with that same unit place, you should get a number either 100 or less than 100. It should not be more than 100. So if you take 5 over here, then you have to write 5 here. So 25 into 5 is 125, and 125 is more than 100. Therefore we'll take 4. If you take 4 here, then you have to write a 4 here. Therefore 24 into 4. We are multiplying this whole 24 into 4, not with the 14. It should be multiplied with the 4 only. So 24 into 4 is 96. And then you subtract it, you'll get remainder 4. So since we have already written a point over here, you take 2 more zeros. So every time when the remainder is left, you have to take down 2 points or 2 zeros. See. And here you'll add 4. Since there is a 4 in the unit place, therefore you add 4 over here. If you add it, you'll get 28. Now again you have to find a suitable number over here, such that when you multiply that with the same number, it should get around 400. Therefore if you write 2 here, and then you have to write 2 over here also. So 282 into 2 is more than 400. Therefore we'll take 1 over here, and if you write 1 here, then you have to write 1 over here also. So 281 into 1 is 281. So subtract it, you'll get 119. And then again you take 2 zeros down. And then here we are in the unit place, we have 1. So you have to add 1 over here. It becomes 282. 1 plus 1 is 2. Take down 8. Take down 2. Again you have to find the number over here. So we'll write take 4 and when you multiplied it with 4, 2824 into 4, you'll get 11,296. So again you subtract it and you'll get 604. So let's take down 2 more zeros, and now here you have to add 4 since there's a 4 in the unit place, so you have to add 4 over here. So when you add it, you'll get 2828. Again you have to find a suitable number over here. So if I take 2, here also you have to write 2, and then you multiplied it, you will get around 56,564. When you subtract it, you'll find that the remainder is not 0 over here. So similarly, you keep on doing this, you'll find that the remainder never becomes 0 over here. And another thing is, you'll also see that the numbers after the decimal points are not repeating. There are a different set of numbers and they are not repeating. So these numbers are called irrational numbers, and the decimal expansion of irrational numbers are non-terminating. At the same time, it is non-recurring, or it is not repeating. So we can classify the decimal expansion of a real number in two major groups: either terminating decimal expansion like 1.2, 1.54, etc., or non-terminating decimal expansions like 1.333, 1.4142, so on. It keeps on going. And non-terminating decimal expansions are further classified into two groups, that are non-terminating repeating decimal numbers such as 1.33. Here 3 is repeating, and the second one is 1.252525. Here 25 is repeating, and in the third example you will see that 3.452452452. So here 452 is repeating. This whole block is repeating. And the other one is non-repeating or non-recurring decimal expansions like 1.412525. So you can keep on writing, but it will not terminate at the same time. The point after the numbers after the decimal points are not repeating. Therefore, those decimal expansions which are terminating as well as non-terminating but recurring decimals are called rational numbers. Or we can say that the rational numbers have either terminating decimal expansion or non-terminating but repeating decimal expansions, whereas the non-terminating, non-recurring decimal expansions are called irrational numbers. Therefore, we can conclude that irrational numbers will have non-terminating and non-recurring decimal expansions, whereas rational numbers can either have, there is a two condition here, they can have terminating decimal expansions or they can have non-terminating repeating decimal expansions. Now in the next one we are going to see the successive magnification method to show decimal numbers on the number line. Let's take an example 1, that is to show 2.345 on a number line. Now this method is only for the rational numbers. Okay. Or you can use it for the irrational numbers given certain conditions like find or represent the decimal up to 5 place of decimal, up to 3 place of decimal, etc. Now so far we have learned about the decimal expansion of a real number, and also we have classified the decimal expansion of a real number into two different parts, that is the decimal expansion of a rational number and decimal expansion of the irrational number. Separately we have already discussed about it. Now in the next portion we are going to learn how to represent these decimal numbers on the number line by using successive magnification method. Let's understand this with the help of an example. First example is to show 2.345 on a number line. And for that, first thing we are going to do is draw a number line, and each point on the number line represents certain numbers. So we'll label them as 0, 1, 2, 3 and 4. Now 0 is the middle one, and here 2.345 is a positive number. Therefore, it lies on the right hand side of the number line. And from left hand side, you can take all the negative numbers, since we don't need negative numbers over here. So we'll take only the positive part of the number line. And now we'll look at the number that is 2.345. And 2.345 is more than 2 and it is less than 3. Therefore, this number 2.345, it lies between 2 and 3. Therefore, what we are going to do is we are going to magnify, that is zoom in this portion of the number line, that is 2 and 3. We'll zoom in this, and at 2 ends we'll take 2 and 3. Now this is the zoom in portion of 2 and 3. Now next thing that we are going to do is we are going to divide this portion or this line segment 2 and 3 in 10 equal parts. And next thing is, now this point represents 2.1, and next one 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8 and 2.9. After 2.9 we'll have 3. So again we'll see that 2.345, it lies between 2.3 and 2.3 and 2.4. Since 2.345 is more than 2.3 and 2.345 is less than 2.4. So this lie between 2.3 and 2.4. Now we are going to zoom in this portion of the number, that is number line, that is 2.3 and 2.4. We'll take the number line and at the two extremes we will write 2.3, and on the other hand we'll write 2.4. Now here again we are going to divide this line in 10 equal parts. So the first one represents 2.31, and then we have 2.32, 2.33, 2.34, 2.35, 2.36, 2.37, 2.38 and 2.39. So now this number 2.345, it lies between 2.34 and 2.35. Since 2.345 is more than 2.34 and it is less than 2.35. Therefore, it lies between 2.34 and 2.35. Again, we are going to zoom in this portion of the number line between 2.34 and 2.35. So here we'll write 2.34 and here we'll write 2.35. Now this is a zoom in portion. Here we have zoomed in this portion of the number line, and again we'll divide the given number line in 10 equal parts. And first one represents 2.341, 2.342, 2.343, 2.345. So 2.343, 44 and 2.345, 2.346, 2.347, 2.348, 2.349 and 2.35. So here now we get the required number on the number line, that is 2.345. Here we are done with the first example. we have shown the number 2.345 on the number line. Now here, since the decimal number are terminating, it's quite easy. Now in the next example, we are going to take another number where the decimal numbers are non-terminating but recurring. That is 4.26 bar on the number line, and in the question it is mentioned that up to 4 place of decimal. You can, in some questions you might be asked up to 5 place of decimal or any place of decimal they can ask. So 4.26 bar is equal to 4.262626 so on. Then 2626 is repeating here. Therefore, in the question we are asked to take only 4 place of decimal, that is 4.2626. That's it. We have to show till here. So again we'll take a number line and we'll label some numbers on it. Here we have taken 0, 1, 2, 3, 4 and 5. Now this number, that is 4.2626, it lies between 4 and 5. 4.2626, because in the question it is asked up to 4 place of decimal, that is 1, 2, 3 and 4. Till 4 place of decimal we have to show. So 4.2626, it lies between 4 and 5. Again we'll zoom in this portion of the number line. That is, we'll write 4 here and we'll write 5 over here, and we'll divide the given line in 10 equal parts. And this one represents 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, 4.7, 4.8 and 4.9, and last we have 5. Now again you have to check, 4.2626 is greater than 4.2 and it is less than 4.3. So 4.2626, it lies between 4.2 and 4.3. So again here we'll zoom in this portion of the number line. Here is the zoom in portion. Here we have 4.2 and here we'll write 4.3. Again you divide the given portions in 10 equal parts. And this first one represents 4.21, and then we have 4.22, 4.23, 4.25, 4.25, 4.26, 4.27, 4.28 and 4.29. So here we'll see 4.262626, isn't it? Now this 4.262626 is greater than 4.26 and it is less than 4.27. So therefore 4.2626, it lies between 4.26 and 4.27. Again here we'll zoom in this portion of the number line. Here you'll write 4.26 and here we'll write 4.27, and again we'll divide this line in 10 equal parts. So after dividing it, you can take 4.261, 4.262, 4.263, 4.264 and so on. And you'll check again 4.2626. It lies between 4.262 and 4.263. Therefore, again here we have to zoom in this portion of the number line. Here we'll write 4.262 and here we'll write 4.263, and we'll divide this line in 10 equal parts and we'll write all the numbers, that is 4.2621, 4.2622, 4.2623, 4.2624, 4.2625, 4.2626, 4.2627, 4.2628, 4.2629, and last one is 4.263. So now here we get the required number, that is 4.2626 on the number line. Done. I hope you have understood this, and in the next slide we have some homework for the students. You take a break for 10 minutes, or you can take a break for 20 minutes and try to solve these questions. Now we have reached the third part of this chapter, and in the third part we are going to learn how to express decimal number in rational number form, or you can say expression of decimal number in the form p by q, where p and q are integers and q not equal to 0. Now here we are going to discuss methods to express decimal numbers in p by q form. And p by q form means we are talking about the rational numbers, and in the earlier part we have discussed about how to express the rational number in the decimal form, and we have also discussed about the decimal expansion of a rational number. And their decimal expansion of a rational numbers are usually classified into two groups. In the first part is for terminating decimal numbers, or the rational number which have a terminating decimal numbers, and we can express these numbers in the form p by q. Let's take few examples, like we have 1.25, 0.37, 3.172 and 3.14524. Now in all these examples you see that the decimal numbers, or the number after the decimal points, are terminating after certain numbers. Now, and the other part is for non-terminating but recurring decimal numbers. And for non-terminating recurring decimal numbers we have examples like, in the first we have 0.3333, and in the second we have 0.373737, and in third we have 3.172172172, and in the fourth one we have 4.253333, so on. So in this example you'll observe that in the first example only one digit is repeating, that is 3. Here only 3 is repeating after the decimal point. And in the second example, you see that the block of 37 is repeating. 373737. So here 2 digits are repeating. And in third example, you'll notice that it's 3.172172172. And again here 3 numbers are repeating, that is 1, 7 and 2. And in the fourth one is slightly different from the previous 3 examples. Here you'll see that it's 4.25333. Here 25 is not repeating. Only digit that is repeating is 3. So here you'll have to apply some different method to express it in the form p by q. Now we'll start off for terminating decimal numbers first. It's quite easy, and since we have learned about terminating decimal to convert into the rational form in the lower classes. Okay, for terminating decimal numbers, let's take an example. Express 0.25 in rational form, or you can say in the form p by q, where p and q are integers and q not equal to 0. So we'll write the solution over here, and we'll take down the number, that is 0.25, which is equal to 25 by 100. And you can cancel these 2 by 5, so you'll get 5 by 20. Again you can cancel the numerator and denominator both by 5, so you'll get 1 by 4. Now this type of things we have learned in lower classes. Here what we did is we moved the decimal point towards the right side. When you move the point towards the right, you add 0 in the denominator. Since here we are moving the decimal point 2 times, that is 1 and 2, so you'll add 2 0 in the denominator, and you'll divide both numerator and denominator by 5, you'll get 5 by 20. Again you divide numerator and denominator both by 5, you'll get 1 by 4, and 1 by 4 is our required answer. Now we'll take a second example, that is to express 3, 4, 2, 5 in rational form or in P by Q form where P and Q are integers and Q not equal to 0. We'll write the solution. We'll take down the number that is 2.3425 and it can be written as 23425 by 10,000. Since here we are moving 1, 2, 3, 4 points towards the right, so we'll add 4 zeros in the denominator. Here you have a common factor 5, so divide both numerator and denominator by 5, you get 46885 by 22,000. And again here you'll have common factor 5, you divide both numerator and denominator by 5, you'll get 937 by 400. And this is our required rational form of the given decimal number. Now we'll move on to the second part, that is for non-terminating but recurring decimal numbers. Now first example is to express 0.222 in a rational form or P by Q form where P and Q are integers and Q not equal to 0. We'll write the solution first, and now in this part you have to follow certain steps to reach the answers. So first step is we are going to take down the number that is 0.222 and it can be written as 0.2 bar. So here one digit is repeating. Now the next step is we'll let x be an irrational number which is of which rational number that we need to find. So we'll let x is equal to 0.2 bar and we'll let this equation number be 1. Since here one digit is repeating after the decimal point, that is 2, so what we do is we'll multiply both sides by 10. So when you multiply you'll get 10x equal to 2.2 bar and we'll name this equation as 2. Now in the first and the second equation you'll notice that the numbers after the decimal point are exactly same. Here we have 2 bar, again here we'll have 2 bar. So when you subtract this, you won't get the decimal numbers, or the numbers after the point becomes 0. So what we do is we'll subtract equation 1 from equation 2. So we'll first write down the equation 2, that is 10x equal to 2.2 bar, followed by the first equation, that is x equal to 0.2 bar, and then we'll subtract it. After the decimal point, all the numbers are same, so you get 0 here. You write down the point, and then 2 minus 0 is again 2. So we'll write down the equal to sign, and 10x minus x is 9x. Since we need to find x, we don't need 9 with x. So what we do is we'll divide both sides by 9. So we'll take down the equation, that is 9x equal to 2, and then we'll divide both sides by 9. Here also divide both sides by 9. So here 9 gets cancelled. So we get x is equal to 2 by 9, and this is our required answer. Or you can say 0.222 ... is equal to 0.2 bar and it's equal to 2 by 9. This is the rational form of the number. Okay, we'll move on to the second example. The second example is express 7.2727 in rational form or P by Q form where P and Q are integers and Q not equal to 0. We'll write the solution. Now in the question, this second example is slightly different from the first one. In the first one, we have seen that after the decimal point, only one digit is repeating. But here, you'll see that 2 digits are repeating. That is 2 and 7 is repeating. So we can write 7.2727 ... is equal to 7.27 bar. Now this bar represents 27 is repeating. So first step is we'll let x equal to 7.27 bar and we'll name this equation 1. So here since 2 digit is repeating, so what we do is we'll multiply both sides by 100. And when you multiply it, you get 100x equal to 727.27 bar. And we'll name this equation as 2. So now in equation 1 and equation 2, you will notice that the digit after the decimal points are exactly same. Therefore, what we do is we'll subtract equation 1 from equation 2. So we'll write the equation 2 first, that is 100x equal to 727.27 bar, and then followed by the first equation, that is x equal to 7.27 bar, and then we'll subtract it. You'll get, since the digit after the decimal points are exactly same, you'll get 0 here, and you write down this point, and 727 minus 7, you'll get 720, and we'll take down this equal to sign, and 100x minus x is 99x. Since we have to find the value of x, we need to remove 99. So what we do is we'll divide both sides by 99. We'll take down the equation, that is 99x equal to 720. We'll divide both sides by 99 here and 99 here. So here 99 and 99 get cancelled. So what you get is x equal to 720 by 99, which is also equal to 80 by 11. Since here both have a common factor, that is 9. So we'll divide both numerator and denominator by 9. And x, this is our required answer. Therefore, we can write 7.2727 dot 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 is equal to 7.27 bar, which is equal to 80 by 11. Now, this is the rational form that we need to find. Now, let's move on to the third example, that is to express 0.4272727 in rational form or P by Q form. So we'll write the solution first. Now in this question, it's different from the previous two examples. In the previous two examples, you'll see that after the decimal point, either one digit is repeating or in the second digit is repeating. That means after the decimal point, every digit is repeating in the first two cases. But here, after the decimal point, we have 4 and then followed by 272727. You'll see that 27 is repeating. 4 is not repeating. Therefore, what we do is, first we'll take down the number, that is 0.42727. It can also be written as 0.427 bar. Here bar is only 27, not 4, because 4 is not repeating over here. Okay, we'll do the first step, that is to let x equal to 0.427 bar, and we'll name this equation as equation 1. And then now what we have to do is we have to move this 4 to the left hand side of the decimal. Therefore, to do so, what we do is here only one digit is there, that is 4. So we'll multiply both sides by 10. We'll get 10x equal to 4.27 bar. And we'll let this equation be 2. Now in equation 1 and 2, you will notice that the decimal numbers after the decimal points are not same. So we need to do one more step over here. What we do is here 27, that is 2 digits are repeating. So we'll multiply both sides of equation 2 by 100. Since 2 digit is repeating, so we'll multiply it by 100. And you will get 1000x equal to 427.27 bar. We'll name this equation as 3. And equation 2 and 3, you will notice that the digit after the decimal points are exactly same. So we'll subtract equation 2 from equation 3, not equation 1 here. Here we'll subtract equation 2 from equation 3. So first we'll take down the third equation, that is 1000x equal to 427.27 bar, followed by second equation, that is 10x equal to 4.27 bar, and we'll subtract it. You'll get, now since the digit after the decimal points are exactly same, so we'll get 0 here, and we'll write down the point, and 427 minus 4 is 423. We'll write down this equal to sign. Then 1000x minus 10x is 999. Now we have to find the value of x. Therefore, we don't need 990. So what we do is we'll divide both sides by 990. So we'll write down this equation first. That is 990x equal to 423. We'll divide both sides by 990 here and 990 here also. So you'll cancel this 990 and you'll get x. And here also you can cancel the numerator and denominator by 3, since 3 is the common factor in both the cases. So you'll get, cancel these two, you'll get x is equal to 141 by 330. Again you can divide numerator and denominator by 3. You'll get 47 by 110. Therefore 0.427277 is equal to 0.427 bar equal to 47 by 110. Now this is our required answer. Hope you have understand. Now the next is the practice portions. So you take a moment and try to express the given decimal numbers in the rational form. The rationalization of the denominator, and under which we are going to study what is rationalization of the denominator, and we are going to learn how to rationalize the denominator. And before going into the detail, we are going to recall some of the very basic algebraic identities and the laws of exponent that we have learned in class 8. Now here I have written the algebraic identities. Here a plus b whole square is equal to a square plus 2ab plus b square, and a minus b whole square equal to a square minus 2ab plus b square, and a plus b into a minus b is equal to a square minus b square, and a plus x into a plus y equal to a square plus x plus y into a plus xy. Now these are the identities that we have learned in class 8, and in this chapter or in this part of the chapter, first 3 identities plays a very important role here. It will be very useful also. And in the laws of exponents, we have studied about 7 laws of exponent, and here we have given an example, a raised to the power m, where a is the base and m is the exponent or power. When the base are same, power are different during multiplication, then what we do is we take the base common and we add the 2 powers. Similarly, while dividing a power m by a power n, then you can write this as a power m by a power n, which is equal to, now base are same, powers are different, so you'll subtract over here. Similarly, when the powers are same, we'll take the power common and multiply the 2 base, and when the powers are same during the division, what we do is we divide the bases and take the power common. When we have a power over a power, then what we do is we multiply the 2 powers, and 6th law is if any number raised to the power 0, then the value is always 1. And the 7th one is a raised to power minus 1 is equal to 1 by a. Now these are some of the important algebraic identities and laws of exponent that will be very useful in the 4th part of the chapter. Now we'll look into we'll try to understand why we need to rationalize, and we'll try to define what is rationalization. Now let's take an example, 1 by square root of 2. 1 by square root of 2, here numerator, that is 1, is a integer, or we can say a rational number, because all the integers are rational numbers, and the square root of 2 is irrational number. And in class 8 we have learned that the square root of any number which is not a perfect square is a irrational number. Since 2 is not a perfect square, therefore square root of 2 is a irrational number. Okay, square root of any number which is not a perfect square is a irrational number. Okay, now next one is, now this square root of 2, 1 by square root of 2, rational by irrational number, is not Now this number is not called a standard form of a number. In the standard form, it is necessary to have a denominator always rational. Denominator, we should write it as a rational. So how to make this square root of 2 in the rational form? Now here we need to think about the number. When you multiply it with the square root of 2, we should get a rational number. So what we do is we'll multiply both the numerator and denominator by square root of 2, square root of 2. So what we get is 1 into square root of 2, and we have denominator square root of 2 into square root of 2. We multiply numerator and denominator by the same number, because while rationalizing the denominator, the final answer should be equivalent to the quotients given here, 1 by root 2. Therefore, when you multiply by root 2 and root 2, the denominator and numerator remains same, because these two get cancelled and it is equal to 1. Therefore, 1 into root 2 and square root of 2 into square root of 2. 1 into root 2 is 2 and square root of 2 into square root of 2 is 2. Now this number is called the standard form of the number. Here the numerator is irrational, but the denominator is rational. In the standard form, it is very important that the denominator should be a rational number. Therefore, we'll take a note here. Now when you multiply square root of 2 by 2, square root of 2, you'll get 2. Therefore, we can say that square root of 2 is the rationalizing factor or RF of the square root of 2. Because when you multiply square root of 2 with the square root of 2, then you get the answer rational, that is 2. So now here you might get the clue what is rationalization. So we'll write here, therefore making the irrational denominator into a rational number is called rationalization of the denominator. Here what we did is, we made the denominator square root of 2, this number square root of 2 into a rational number, that is 2. And these two numbers are equivalent, or we can say same. So this is called rationalization. And very important thing is why we need to rationalize a number. Why we cannot leave as it is. Because in the standard form of a number or any number, the denominator should be a rational number. Otherwise, it is not called a standard form. Therefore, to make the number in the standard form, it is very important to rationalize it. Let's take another example. For example, we have a 1 by square root of 5 minus square root of 3. Now we have to, now here also numerator 1 is a integer or a rational number, and square root of 5 minus square root of 3 is a irrational number. Now we have to think about a number such that when you multiply that particular number with the square root of 5 minus square root of 3, it should give a rational number. So here now we have a very recall an algebraic identity, that is a plus b into a minus b is equal to a square minus b square. So what we do here is, here we have square root of 5 minus square root of 3. If you multiply it with the square root of 5 plus square root of 3, you will get square root of 5 square minus square root of 3 square. Here we have used this identity. Instead of a, we have square root of 5. Instead of b, we have square root of 3. So a minus b into a plus b is a square minus b square. And the root and the square get cancelled over here in both the cases. So you will get 5 minus 3. And 5 minus 3 is 2. And 2 is a rational number. And 2 is a rational number. Therefore, here what we do is we'll multiply both the numerator, that is 1, and denominator root 5 minus root 3 by square root of 5 plus square root of 5 plus 3, square root of 3. So you multiply numerator 1 into square root of 5 plus square root of 3, and the denominator becomes here. We have already calculated over here square root of 5 minus square root of 3 into square root of 5 plus square root of 3 is root of 5 square minus root of 3 square. That is, we are using the algebraic identity here. And further, when you multiply a number, so you get root 5 plus root 3 divided by, and square root and square get cancelled, we get 5 minus 3. So we'll again copy the numerator, and 5 minus 3 is 2, and 2 is a rational number. Therefore, the given number, that is root 5 plus root 3 by 2, is a standard form of writing a number. Now here again we'll take a note. Square root of 5 minus square root of 3, when you multiply it with the square root of 5 plus square root of 3, you'll get answer 2. Therefore, we can say that square root of 5 plus square root of 3 is the rationalizing factor, or RF, of square root of 5 minus square root of 3. Or in the other word, we can say square root of 5 plus square root of 3 is the conjugate of square root of 5 minus square root of 3. When you talk about the conjugate, we'll change the operation between the two numbers only. So I hope till here you have understood. Now we'll move on to do some example questions. Okay, here we have find the rationalizing factor in each case. Till now we have defined we have defined the rationalization of the denominator, and we have also discussed that why we need to rationalize the denominator, and we have come across a new term that is called the rationalizing factor or conjugate. These 3 points are very important to be noted. And now in this worksheet, we'll find the rationalizing factor in each cases. We'll take a column. In the first column, I'll write the irrational numbers, and in the second column, we have to find the rationalizing factor of the given irrational number. Okay, first one is square root of 10. We have all the irrational number in the first column. Okay, now the first one, that is square root of 10. Now we have to think about a number. When you multiply it with the square root of 10, it should yield a rational number. So we'll do a rough work here. Since square root of 10 into square root of 10 is square root of 10 square, which is equal to 10. And 10 is the rational number. Therefore, rationalizing factor of square root of 10 is square root of 10. Next one is 4 root of 3 plus root 5. Now, what is the rationalizing factor over here? So here we have to take the conjugate of this number. We'll solve here. So that is 4 root 3 minus square root of 5. So we'll prove it over here. 4 into square root of 3 plus root of 5 into 4 into square root of 3 minus square root of 5. Here again you will use the algebraic identity here, a plus b into a minus b. You will get a square, that is 4 root 3 whole square, minus root of 5 square. Here 4 square is 16 and root 3 square is 3 minus root of 5 square is 5. Therefore, you will get 48 minus 5, which is equal to 43, and 43 is the rational number. Therefore, the rationalizing factor of 4 root 3 plus root 5 is 4 root 3 minus square root of 5, or conjugate. So here you will notice that only the operation between the two numbers changes. Here plus becomes minus. In the third example, we have root 3 minus 10 root of 5. Here again we'll try to solve it over here. Root 3 minus 10 root of 5 into root 3 plus 10 root of 5. So here we are multiplying the given number with the conjugate of this number. We'll get here, we'll use the algebraic identities a minus b into a plus b, that is a square root 3 square minus b square, that is 10 root of 5 whole square. Root 3 square and square root get cancelled. We'll get 3 minus, and 10 square is 100 into root 5 square is 5. Therefore 3 minus 500 will get minus 447, and minus 447 is a rational number. Therefore the rationalizing factor of root 3 minus 10 root 5 is root 3 plus 10 root 5. I hope you have understood till here, and I want you to complete the remaining 4 questions. Now we'll move on to the example questions. Okay, how to rationalize the denominator. Now the level 1. Now level 1 is the simplest type of questions. Here the question says to rationalize the denominator in the following cases. We have A 2 by root 5, B 60 by 7 root 10, and C equal to minus 6 by root 12, and D equal to 7 by 2 root of 14. I'll do the first 2 examples, and I want you to do the third and the fourth examples. Okay, we'll start with A, that is solution. A equal to 2 by root 5. Now here the rationalizing factor of square root of 5 is square root of 5. Therefore we'll multiply both the numerator and denominator by square root of 5 and square root of 5. So you'll get 2 into root 5, and square root of 5 into square root of 5 is square root of 5 square. So you'll get 2 root 5 by square and root get cancelled, we'll get 5. Therefore this is our required answer. We can prove that root 5 into root 5 equal to root 5 whole square, which is equal to, root means power of half. So 5 raised to power 1 by 2 whole raised to power 2 is equal to, now we have power over power, so we will multiply the 2 powers. Half into 2 is 1, therefore you'll get 5. Now in the second example, that is B. Okay, here we have used this law of exponent. Now this second example, that is B is equal to 60 by 7 root 10. Now here the rationalizing factor, now we have to only rationalize the irrational number. So what we do is we'll multiply both the numerator 60 and denominator 7 by root 10 by root of 10 and root of 10. When you multiply it, you get 60 into root 10 by 7 root 10 into root of 10, which is equal to 60 root 10 by 7 into, here we have root 10 into root 10, therefore root 10 square, and 7 root 10 into root 10 is equal to 7 into root 10 square. Here we have got this, and 7 into root of 10 square is 10 raised to power half whole square. Root means power of half. Therefore power over power, again we'll use this identity here. So you'll get 7 into 10 raised to power half into 2, and 2 and 2 get cancelled. So you'll get 7 into 10, that is 70. So you'll write 60 into root 10 by 7 into 10, which is equal to, now here again you'll cancel the numerator 60 and denominator 10 by 10. 10 6 is 60 and 10 1 is 10. So final answer you'll get is 6 root 10 by 7. Now in the final answer you'll see that denominator is a rational number. Therefore we have rationalized the 60 by 7 root 10 as 6 root 10 by 7. Now next one is the level 2 types question. Rationalize the denominator in the following cases. Here we have some questions. A equal to 2 by root 5 minus root 3, and B equal to 60 by 3 root 10 plus root 5, and 7 by 2 root 12 minus root 10, and D is the 3 by square root of 11 plus square root of 2. Now this is the level 2 type question. I'll do the first and second one, and you'll do the C and D. Okay, first solution, that is A equal to 2 by root 5 minus root 3. Now here we have to again think about rationalizing factor of square root of 5 minus square root of 3. So the rationalizing factor of square root of 5 minus square root of 3 is the conjugate of square root of 5 minus square root of 3, that is square root of 5 plus square root of 3. So we'll multiply numerator and denominator by square root of 5 plus square root of 3 and square root of 5 plus square root of 3. Here instead of minus we have taken plus. So you multiply it, 5 into bracket square root of 5 plus square root of 3 will multiply this, and in the denominator we can use the algebraic identity, that is a minus b into a plus b. So a plus b into a minus b equal to a square minus b square. Therefore you will get 2 into root of 5 plus root of 3 and a square, that is root 5 square minus root 3 square. So you copy the numerator, 2 into square root of 5 plus square root of 3. So square and root get cancelled over here. You will get 5 minus 3, and 2 by square root of 5 plus square root of 3, and 5 minus 3 is 2. Therefore here 2 and 2 get cancelled. So the answer you get is square root of 5 plus square root of 3. Here denominator is 1. So it's a denominator is a rational number. Therefore, we have rationalized the first question. And this is our required answer. Okay. In the second one, that is 60 by 3 into square root of 10 plus square root of 5. Again, we have to find the rationalizing factor of 3 root 10 plus square root of 5. That is 3 root 10 minus square root of 5. So we'll multiply both numerator 60 and denominator 3 root 10 plus root 5 by 3 into root 10 minus root 5 by 3 into root 10 minus root 5. Here, please note this. Instead of plus, we have taken minus over here. Otherwise, all the numbers are same. So such numbers are called conjugate. Or we can say 3 root 10 minus root 5 is the conjugate of 3 root 10 plus root 5. Or you can say a rationalizing factor. So we'll multiply this. We'll get 60 into 3 root 10 minus root 5, and in the denominator we have used the identity a plus b into a minus b. So you'll get 60 into 3 root 10 minus root 5 and a square, that is 3 root 10 whole square, minus b square, that is root 5 square. And now here I have shown how to multiply this square. So 3 root 10 whole square now means 3 into root 10 into 3 into root 10, meaning of 3 root 10 whole square. So what we do is we'll multiply 3 and 3, 3 into 3 into, we have 2 root 10, therefore it becomes root 10 square, and 3 is 9, and square root of 10 square is 10, therefore 9 into 10 is 90. So we'll write over here 60 root 3 10 minus root 5 by 9 into 10 minus 5. Therefore 63 root 10 minus root 5 by 90 minus 5. 9 10 is 90. 90 minus 5. And we'll again write this. Copy the numerator, and 90 minus 5 is 85. Since 60 and 85 has a common factor 5, so we'll divide both the 60 and 85 by 5. So you'll get 60, 5 12 is 60, and we'll write all the numbers in the bracket here, and 5 17 is 85. Now here we cannot reduce it further, therefore this is our required answer. And here also you will see that the denominator is a rational number, hence we have rationalized the 60 by 3 root 10 plus root 5. Okay, now we'll move on to the level 3 type questions. Rationalize the denominator in the following cases. Now here you will find the irrational number in both numerator as well as in the denominator. And again I'll do the first two examples, and I would want you to do the question C and D. Okay, first solution. Root 5 plus root 3 by root 5 minus root 3. Now we have said that in the topic itself, it is rationalizing the denominator. It's not about the numerator. Numerator, we can have an irrational number as well as rational number, anything. But denominator should be a rational number. So we care only about the denominator, not the numerator. So here in this question, you have to find a number which, when multiplied with square root of 5 minus square root of 3, it should give a rational number. So we'll write, or we'll multiply the numerator and denominator both by conjugate of root 5 minus root 3, or we'll multiply numerator and denominator by the rationalizing factor of the denominator. That is root 5 plus root 3, root 5 minus root 3. We have copied the question here, and we'll multiply numerator by conjugate of the denominator, that is root 5 plus root 3 and root 5 plus root 3. So here again it looks similar, the both in numerators are similar, root 5 plus root 3, root 5 plus root 3. So here you can use the identity a plus b whole square. Therefore square root of 5 plus square root of 3 whole square. And in the denominator, we can use the third identity, that is a minus b into a plus b, that is a square minus b square. Here we have used a plus b whole square equal to a square. Now we'll use this identity. So root 5 plus root 3 whole square, it becomes a square, that is root 5 square, plus 2ab. We'll write 2. Instead of a we have 5, instead of b we have root of 3, plus b square. Instead of b we have square root of 3 whole square. And in the denominator we have used the identity, that is a plus b into a minus b equal to a square minus b square. Further, square root of 5 whole square is 5, because root and square get cancelled, plus 2 into, in the root we can multiply the two numbers, but we cannot add 2 root, but we can multiply the 2 root. So we'll take the root common and we'll multiply 2, 5 and 3, plus, and root of 3 square is square and root get cancelled, we get 3. So in the denominator again root and square get cancelled, here also root and square get cancelled, you'll get 5 minus 3. So 5 plus 3 will take them together, plus 2 root of 15. 5 3s are 15. So 5 minus 3 is 2. And we'll add these two numbers, that is 8 plus 2 into square root of 15 by 2. And here in both the term, in the first term and the second term, we have 2 as a common factor. So what we do is we take out 2 common, and then it becomes 4. 2 4s are 8, plus 2 into square root of 15 is 2 root 15. So we have taken 2 common outside, and we cancel these 2. 2 and 2 get cancelled. We get answer 4 plus square root of 15 is our required answer. And here the denominator is 1. Therefore, it's a rational number. Okay, now the next example, or the B, that is square root of 10 minus square root of 3 by 3 root of 10 plus root of 5. This is a bit different from the previous example, that is A, because in the A we have seen that the numerator and denominator have the same numbers, except they have the different operations. So here the numerator and denominator are not exactly same. So what we do is, again we have to find the rationalizing factor of the denominator. The rationalizing factor of the denominator, 3 root 10 plus square root of 5 is 3 root 10 minus square root of 5. So we'll multiply both the numerator, root 10 minus root 3, by 3 root 10 plus root 5 by 3 root 10 minus root 5, 3 root 10 minus root 5. Now here we cannot use the identity in the first case, in the numerator, sorry, because numerators are not same. Root 10 minus root 3 is not equal to 3 root 10 minus root 5. Therefore, we cannot use any identity here. But in the denominator, we can use the third identity, that is a plus b into a minus b. So, how we do the numerator? We'll multiply square root of 10 with this whole portion, that is 3 root 10 minus root 5, and root 3 should multiply this whole portion again. So we'll write it as root 10 bracket into, that is 3 root 10 minus root 5, will copy the same number, and minus root 3, here minus root 3 into 3 root 10 minus root 5. So in the denominator we use the identity, that is a square. Instead of a we have 3 root 10 a square, minus, in the denominator instead of b we have root of 5, so root 5 square. So when you multiply it again here, root 10 should multiply both the numbers. Okay, now in the denominator we have used this identity. Now we'll multiply this in the numerator. So root 10 should multiply 3 root of 10, and root 10 should also multiply with square root of 5. Similarly, this minus root 3 should multiply with 3 root 10, and this minus root 3 should multiply with minus square root of 5. So here we get root 10 into 3 root of 10. Now here root 10 is plus, so plus into minus is minus, root 10 into square root of 5. So minus into plus is minus, root 3 into 3 root of 10, and minus into minus is plus. Now here very important, sign, multiplication of the sign. Minus into minus is plus, so root 3 into root 5. And in the denominator we get 3 square is 9, and root 10 square is 10, and minus root of 5 square is 5. So we'll multiply this, 3 into root 10 square minus root of 10 into 5, minus we have 3 here, we'll write down the 3 first, into root 3 into 10, because root 3 and root 10, we take it together, root of 3 into 10, and plus root of 3 into 5. So in the denominator we get 90 minus 5. Again we'll write 3, root 10 square is 10, minus 10 into 5 is root of 50, minus 3 into square root of 3 into 10 is 30, plus square root of 3 into 5 is 15. You will write it again, 3 into 10 is 30, minus square root of 50, minus 3 root of 30 plus square root of 15 by 90 minus 5 is 85. Now here we cannot take any common from the numerator and in the denominator, so we cannot cancel anything over here. Now we are done here, and I want you to do the exercises that I have mentioned in each level, and also try to solve the textbook questions. Thank you.